Stokes theorem says that the flux of the curl of a vector field is equal to, over a surface, is equal to the line integral of the original vector field over the boundary. And now, one thing that may or may not be obvious, but we can make it even more explicit, is that the boundary has to be a closed curve. And so we include a circle on the line integral to say we're integrating over a closed curve. And furthermore, this closed curve has a specific orientation, and in quote, positive orientation means it has to agree with the orientation of the surface. And so in general, we do a positive orientation by saying that it's going counterclockwise from some point of view, whichever way it's going. Another way to view this positive orientation idea is to look at the idea of walking around the curve and so perspective here kind of gets a little messed up and blurred here. So another perspective would be to take a look at a surface with, in this case, an upward orientation. And so if you were to be some guy walking around the boundary of the surface, with an upward orientation, so you as a guy walking around is going to be the same orientation as the normal vector, and as you walk around that surface, your left side would be on the surface on top of the orientation, where the orientation is. So this is a little trickier to draw, but now if we're going downward, so this arrow is technically inside of this surface, then you walking around the surface as you walk around the surface in the same direction as the normal vector, I mean your head is in the same direction as the normal vector. Then as you walk around that surface, your left side should be where the surface is. So you should be walking in this direction. Okay? All right, so as we take a look at some examples, I'll see if I can quickly draw the surface and then draw the curves with their orientations on a graphing program. So let's do some examples. Let's do this one. It says use Stokes theorem to evaluate this problem. And so if we're using Stokes theorem to evaluate this problem, they're giving us one side of Stokes theorem and we have to evaluate the other side. So this is another thing about these theorems, the Stokes theorem and the other one that we're going to talk about, or even Green's theorem, is that you're asked to compute an integral, and then you have to identify what kind of integral that is. And here in this particular problem, they're asking you specifically to use Stokes Theorem. So if you do that, then you know that you're going from a flux of a curl to a line integral. So Stokes Theorem says that this should equal to the line integral of the boundary of S of your vector function dotted with the little s, or I think we use r. Now we have to figure out what r is equal to, that curve with a specific orientation. So here you have a hemisphere. This is where we get to see our first application of how this orientation is going to work. You have a hemisphere, and then you want an outward orientation. So as you get closer and closer using the right-hand rule, or however you want to look at it, it looks like we should be going in a counterclockwise direction from the top, if you view it from the top. So that would be the orientation. So that means if I ignore the surface itself and just focus on the curve, because that's what I'm going to end up doing, my curve is going to be spinning around in a counterclockwise direction, and it's flat on the xy plane because that's where the boundary is. Yeah?
So if the orientation is upward, and in order for it to be upward, so then it's moving clockwise, or is it just that case only?
Well, if it's going from the top like this, then it's going to spin around in a counterclockwise direction if we look at it from the top.
Oh, okay.
So this is close to a sphere, and this is your spinning right-hand rule orientation. And if you're going this way, as you get closer and closer to the bottom, you'll see that it's going to be spinning this way. And if I look at that from the top, then it's the counterclockwise direction. Oh, broke. So that's going to be our orientation, and that's going to give us a parameterization. Well, that's going to lead us to a parameterization where we can define whether it's orientation preserving or reversing. So I think this is, since it's going clockwise or counterclockwise, this is our standard circle parameterization. So your curve C, also known as the boundary of S, can be, and this is a curve, so this is just parameterizing one dimension, and this is just going to be cosine and sine with a radius of 5, it looks like, right? And since we are dealing with this in 3 dimensions, and we only really have 2 dimensions, then the z component must be equal to 0. And then if we take this from 0 to 2 pi, then we've completed that whole thing. Yeah? Based on the shape of the curve, yeah. So you're going to need to parameterize circles. You're going to need to parameterize line segments, and pieces of a curve like a parabola, a piece of a parabola. You should be able to parameterize those curves, and then you should be able to parameterize a handful of surfaces as well. All right, so instead of taking the curl of this, we're going to take the line integral of the original vector field. So our line integral will be over the boundary. So this is f dotted with dr. And f is equal to this. And then I'm going to dot it with the derivative. I guess I'm going to need a little bit more space here. R prime of t is equal to negative 5 sine t, positive 5 cosine t, and 0. So the good news is that when I dot that, the 0 component will disappear. So this is going to be an integral of, and I'm going to replace things a little bit later, but for now I'm just going to plug in the vector field. That's 4y cosine z e to the x sine z and x e to the y, dot that with negative 5 sine t, 5 cosine t, and 0. dt. Now, this is not really a good way to set this up because I have x's and y's and z's and t's. But let's take a look at, first of all, let's take a look at the dot product. Should we look at the dot product first? Well, this is f right now. But what you need to do is you actually need to evaluate this with r of t. All right? So that means your actual function is going to be, well, the interesting thing is that z is equal to 0. So this would be 4 times y. What's y? Y is equal to 5 sine t times cosine of z. So that would disappear. Oh, that would become 1. I have e to the x, e to the x. X is equal to 5 cosine t times sine z, and z is equal to 0. And then I have x e to the y, so I don't really want to write this down, but I will. X is equal to 5 cosine t times e to the y is 5 sine t. So that's what that f, that's what the first vector becomes. Let's see if we can simplify it a little bit. This is just going to be equal to 1. This is going to be equal to 0, so that knocks out this whole term. And then this is going to be whatever that is. So this is 20 sine t, 0, and I'm just going to put star for this last one because I'm going to dot it with something that's going to be 0 in the z component. So that's eventually going to go away too. So now let's see. Let's rewrite this integral. Integral from 0 to 2 pi. 20 sine t, 0, and star dotted with minus 5 sine t, 5 cosine t, and 0. And so this last term disappears, the middle term disappears, so I have 20 times 5, that's negative 100. Sine squared t dt. which is not the easier of the trig integrals. So I'm going to have Wolfram Alpha find it for me. Negative 100 pi. So that should be the answer. Any questions? Let's try. This is a scary part, right? Okay, that's a good start. Any questions with the idea? Okay, let's do another problem. Let's just do a whole bunch of problems. Uh-oh, here's my... So this next one takes Stokes Theorem and has you work with it the other way. In the previous problem, we looked at Stokes Theorem by finding the integral of the surface integral or the flux of the curl. Here they're giving us a line integral. And C is oriented clockwise viewed from above with a triangle of vertices that's equal to this stuff. So if we're supposed to use Stokes Theorem for this problem, what we need to do is we need to take a look at this and say, okay, instead of doing a line integral, I'm going to do a flux integral of S. Now S is going to be the surface. The surface. Where is the surface? Well, let's think about that in a few minutes. But we want the curl of the vector field be S. So we have a couple things to think about. First of all, we probably should figure out the curl of F. Second, we have to figure out what that surface is. So let's take the curl of F first. So remember how the curl goes. We have to do the partials here. And I would put d dx with partials, but I'm just going to say d sub x, d sub y, d sub z. And just to say I'm going to take the partials of this. And then I have x plus y squared, y plus z squared, and z plus x squared. And so I should come out with a vector when I take the curl. And the first one is going to be the derivative of y, or the derivative of z plus x squared with respect to y. That's 0. Minus the derivative of y plus z squared with respect to z. So that's 2z. And then the middle term is going to be negative. I'll put negative there. The derivative of z plus x squared with respect to x minus the derivative of x plus y squared with respect to z. Kind of seeing a pattern here. And then the last one, the derivative of y plus z squared with respect to x, and then the derivative of x plus y squared with respect to y. Yeah. Well, it depends on how you do your curl. When I do my curl, the I is negative. When you do a cross product, remember the middle term should be subtracted. So that looks like it's the curl, so that's the vector field I'm going to integrate, I'm going to take the flux of. Now S, what is S? Let's move to this geometry of this thing here. I have vertices at 9, 0, 0, 0, 9, 0. So if I was to do a line integral, viewed from above with the counterclockwise direction, if I was to do a line integral, I would need to do 3 line integrals for this, which is not impossible, but it certainly would be a little bit more difficult. But now I need to create a surface in here. So it looks like, can you guys see a surface here? It looks like a plane would work, right? Boy, it would be really nice if I knew the equation to this plane. So the equation of the plane is x plus y plus z is equal to 9. But let's actually find it using some of the techniques that we've learned in the past. And what we can do is we can find a normal vector. So what do we need for an equation of a plane? We need a normal vector and a point. So we have 3 points to choose from. So now just to find a normal vector, what we might need to do is we might need to find a couple of vectors on the plane and then cross it, and then we get a normal vector, right? So let's do that. Let's find a couple of vectors on the plane. So this vector might be a good vector. It's head minus tail, so it's 0, 9, 0. Maybe I'll label this first, and then I'll just 0, 9, 0, minus 9, 0, 0. So this vector, one of the vectors is going to be minus 9, comma 9, comma 0. Right? Let's have another vector. Over here, and that vector would be head minus tail. It would be 9, comma 0, comma minus 9. Right? Now, negative 9, 0, positive 9. Okay? And then now I want to cross it. I want my orientation. Which way should we have our orientation going for the surface? Do we want it going up? Coming out, right? Coming towards you. So I would cross it by crossing this first one and then the second one. Yeah.
If our normal vector was pointing out the other way around, it would be the first one over here cross with the second one instead of the cross with the second one and the first one.
Yeah.
Okay.
Yeah. So we're going to cross in this order. So we're going to cross by doing this. So I'm going to call this, what should we call it? Let's call it capital N. And the first vector we want to cross is negative 9, 9, 0, and then negative 9, 0, 9. So we cross that, and we're going to get 81, comma, negative 81, comma, negative 81. Okay. Now, if you remember, this is going to be the normal vector throughout this whole plane, right? It's a plane, so the slope or the normal vector is not going to change anywhere. So it's going to be the same. So I'm starting to get interested in having the flux integral look like this instead of the other way, right? So all we need to do is we need to identify your normal vector, your unit normal vector. And what is that going to be? No. I was going to say 1, 1, 1, but it's not. It's 1 over root 3. So you have to square each one and divide by it to put all under square root. So I think it's going to be this. Maybe. Yeah. Okay, good. So that's my normal vector. I have the curl, I have my normal vector, and I have the surface. My surface. Do I have the surface? I don't have the surface yet. I got distracted. What's the surface? Yeah? Yeah. So I didn't continue. I didn't finish looking at the plane here. So the plane is going to be 81 x minus. We can pick any point, right? So let's pick the 0, 0, 9. X minus 0 plus 81 y minus 0 plus 81 z minus 9 is equal to 0. So this is an equation. I can really just cancel out the 81s, right? Factor it out and cancel it. So I have, what do I have left? I have x plus y plus z minus 9 is equal to 0. Okay, So now I'm going to integrate this over the surface. So this has now just become a surface integral. I still need the surface area component, which is just going to be constant. So our parameterization for this is going to be R of xy is equal to x, comma, y, comma, and then I would solve for z, which is going to be 9 minus x minus y. And then my surface area component is going to be do you remember how this is going to go? It's fx squared, fy squared, except this is your f right here. So the derivative of this with respect to x is 1, right? Or negative 1, but you're going to square it, so it doesn't matter. So fx squared plus fy squared plus 1 squared. Remember that? So that's your surface area component. So in this case, it's just square root of 3. Right? All right, so that's going to be our ds. Let's see what we got. Let's take a look at f dotted with. So let's take a look at this curl. And let's evaluate it at r of xy. So this is going to be negative 2z. What's z equal to? Z is equal to this. Comma minus 2x. And x is just equal to x. Comma minus 2y, and y is just equal to y. And then we're going to dot that with the normal vector. So let's see. Minus 81 plus 2x plus 2y, comma minus 2x, comma minus 2y, dotted with the normal vector. I'm going to take out a 1/3 so I don't have to write 1/3 a bunch of times. Okay, so if I combine all this, I'm going to get a 1 over root 3, and then I have minus 81 plus 2x plus 2y minus 2x minus 2y. Wow, that simplifies things. So I just have negative 81 left, right? So that's my integrand. My ds is going to be root 3 times dA. So this is going to be the integral. Oh, I need to figure out my region. Let's talk about that after I set this up. Of negative 81 over square root of 3 times square root of 3 times dA. So this is your curl dotted with a normal vector, and this is your ds. Yeah? This, you mean how did we get this, or how did we get this?
How did we get
This thing?
yeah, why did you just choose X and Y?
Yeah, just, no, well, not randomly. X and Y would be the X and the U and V parameterization. So it's the X and the Y, and then your Z is going to be this thing. We didn't talk about the region that we're going to integrate over D. So let's go back to our picture. And since this is a graph parameterization, when we're looking at the image in X and Y, did I do something wrong? Oh, 9 times 2 is not 81? Ah, I think I told my kid the wrong thing then. Good? Thank you. All right. Back to our region. We need to figure out our domain, D. So D is going to be some region that we need to be able to describe using integrals. So we're going to do the double integral thing where we go into the region and get out of the region with respect to, doesn't matter, but I chose Y first. And then with respect to X will be constants. This is 9, so I know my X is going to go from 0 to 9. With respect to Y, I'm going to get into the region at 0, and then I'm going to get out of that region of this line. This line, by the way, is what? 9 minus X. That's when Z is equal to 0, right? So if you look at the plane, set Z equal to 0, and then you have X plus Y is equal to 9. So Y is equal to 9 minus X. So this is our domain. All right, well, actually, I don't even know if we need that. Because these are all constants. Root 3 and root 3 would cancel. I have a negative 18. I'll have a double integral of D, dA, and D is that triangle. And you know when you have a double integral where your integrand is 1, this is just going to equal to the area of D, which is a triangle. Height, base is 9, height is 9, right? I do so. So, a right triangle. Oh, no. So the height 9, base 9, so I have negative 18 times 1/2 base times height. Where's that 81? There's a bunch of 81s somewhere else too. So 9, 9, and 9. What is that? 9 cubed. Okay. Well, that was easy. Any questions? Let's see if we got it right. Oh, the exact number. I was going to put 9 cubed. I actually have to know what 9 cubed is. What is it? I do what? 273? Did you say I think? Jeez, guys, come on. What? 729? Two for two. Woo! Okay. So we didn't have a surface, right? We're looking at a line integral. We didn't have a surface, and so we made up a surface whose boundary is that triangle. And from there we went from, instead of doing 3 line integrals, which is what we would have done, we would have had to do, instead of doing 3 line integrals, we did 1 flux integral. We did 1 flux integral. And the first thing we did was find the curl. And then once we found the curl, we know that that's going to go inside of our integral. And then we found the surface. So we made a surface. We made a plane out of these 3 sides, or the 3 vertices, 3 sides. So we made this triangular region of a plane, and we found a normal vector. So once we found a normal vector, we thought, well, that's good. We can use this form. We can use this form of the flux integral, and we'll dot it with the normal. And now we have to go back and find our ds. Remember that we're integrating over surface area. And so this formula is going to come in really handy for us. It keeps coming back. So it's always good to keep that in mind. This is our surface. When we're integrating with respect to surface area, this is our surface area element. Kind of like the magnitude of r prime would be our path integral element. And then we do our dot products, and then we put this together into our integral. And then we integrate over that. So if this thing in here didn't happen to be 1, then we would have needed to put these limits in here and did a double integral. But the fact that this is 1 means that we can take advantage of that special formula or special property that we're really just looking for the area. Questions? Yeah. Yeah, so this has to be a unit vector. So we found a normal vector. It was constant. It's great to have constant normal vectors, and then you just shrink it down to a unit vector, and that's what you get to use here. Okay? All right. So we have to be familiar with doing flux integrals and line integrals and stuff. And so, in fact, I'm going to give you guys a quiz tomorrow, a take-home quiz tomorrow, where I want to see the work. I was thinking about just having you guys do a quiz online, but all you do is put the answer there. I actually want to see the work that you do to create the integral and to have it a working integral that you can actually integrate. So I'll make it as 2 quizzes, and I'll I'll probably have you guys download it on the computer instead of printing it out. You print it out. Okay, so Stokes integrals. So Stokes theorem allows us to move from a line integral to a flux integral, or from a flux integral to a line integral. Let's see. There's a verify where you have to do both sides. Oh, maybe I'll have you guys do that instead. Just do a verify, so you do both a line integral and a flux integral. Line integral lies between plane. All right, let's. We can either do. Oh, we might have time for two. Let's take a look at this one. So it says to use Stokes theorem to evaluate the line integral. So this is a line integral, right? It's a single integral over a curve of f, where C is the intersection of the hyperbolic paraboloid and the cylinder oriented in the counterclockwise direction from above. So we want this line integral to become a flux integral. And then we want the orientation to be counterclockwise from the top. So imagine this is a cylinder. Well, they tell you it's a cylinder. This is a cylinder, and then you have this hyperbolic paraboloid, which is that Pringle chip. I'm not going to try to draw it. And we want to, oops, this is an S. So the surface that we would probably want to use is the hyperbolic paraboloid. And so if you're looking at it from the top, and I'm not going to draw a hyperbolic paraboloid, but let's just say this is the hyperbolic paraboloid. If you're looking at it from the top and it's going in a counterclockwise direction, and then let's say this is the hyperbolic paraboloid in here, which way should the normal vector be pointing for the hyperbolic paraboloid? Up or down? Should be going up, right? So the not so good thing about this is that since this is a hyperbolic paraboloid, these vectors would be not going directly up, and it'll be changing depending on where you are on the surface. So I might want to stick with this instead of the dot end business. And so I think last time we did the curl first, so maybe we should be consistent here and do the curl first. Let's find out what the curl of f is. And I want the partial with respect to x, the partial with respect to y, the partial with respect to z. That's my notation for it. And then my x component is x squared y. My y component is 1/3 x cubed. And my z component is xy. Okay, so let's take the curl. In the I direction, it's a derivative of xy with respect to y minus the derivative of something with an x with respect to z. There's no z's in there, so that's going to be 0. I'll put a negative in front there. The derivative of xy with respect to x minus the derivative of this thing with respect to z. Again, there's no z's in there. And then the last component would be the derivative of this thing with respect to x. That would be x squared minus the derivative of this thing with respect to y. That would be x squared again. So conveniently, it disappears. So the curl is going to be x comma minus y comma 0. Okay? All right, now let's parameterize your S. S is going to be equal to this. Well, that's a simple parameterization. Again, we'll use the XY graph parameterization. X is x, y is y, and z is equal to y squared minus x squared. Okay. Now I want the normal to the surface, so Rx cross Ry, and I'm not going to take the magnitude of that because I'm just going to plug that in as my ds. And this is going to be, it depends on how you cross it, right? I think the way this is going to cross where x is first, it's going to be negative 2x negative 2y and positive 1. Right? If we kind of view this as your f of xy, I have a negative fx, negative fy, positive 1. Remember we did that a long time ago? Define the normal vector. Is this the right orientation? And how can you tell if it's the right orientation? Any ideas? So when you get to this part over here, this is where you get to check if you have the right orientation or not. What? So how do you know if it's the right orientation? Yeah?
Wasn't there like some trick that you showed us last time where if the two of them are negative, then it's
If two of them are negative, then the last one's positive, and vice versa. But look at the red arrow on the surface, and look at the vector that we came up with. Positive. What's positive? The z component's positive, right? So the z component is positive, so and we want this to be pointing upward, so that is going to be the correct orientation. So we'll say OPP because we got the positive orientation here. Okay, so we got the curl and we got the cross product, so I think we're ready. We're almost ready. We need to figure out what the domain is. So remember that this is going to be reduced from a flux integral to a double integral, but we still need to figure out what the domain is. So what's the domain? So your domain is going to be, it's within the cylinder, and so that circle would be the shadow that this is going to cast on the xy plane. So we can't always get lucky and have a constant inside. But after we dot this, we get an x squared plus y squared, and we're dealing with circles, so polar coordinates would be great. All right, so let's go polar here. Our domain is going to be represented with r going from 0 to 1, theta going all the way around. And our integrand is going to be 2r squared. So that's just the integrand, but the dA has another r. So that'll end up being r cubed. And there's no thetas, so we can separate this. Let's take the 2 all the way out. Let's integrate from 0 to 2 pi with respect to theta. That's just going to be 2 pi. And then the integral from 0 to 1 of r cubed is going to be 1/3. So we got 2 pi.
I just realized that basically before we evaluate r, when you integrate it, but before you evaluate the r, it's the formula for sphere.
Yeah.
For volume of sphere.
R to the 4th over 4. Yeah, I lost that one too. All right, so that would cancel. It would just be pi. All right, 3 for 3, you think? So this has a radius 1. So we're looking for a cylinder radius 1. That would be one of these big ones. And we need the orientation of the I'm just going to guess. Need the orientation of the paraboloid. Oh, find a parametric equation for C. I'm not going to do that. Let's just see if our first answer is correct. Okay, so that one's right. So we could think about, you could think about how the saddle is oriented to figure out which one of these two. I think it's either this one or this one. Obviously, it's this one now since we got that one wrong. And then here they want you to try to parameterize the equation. So that's an interesting problem. I'll let you think about that. But think about the r is equal to cosine theta and y is equal to sine theta, and then put that into the z to give a z component. All right, I was hoping to do one more, but I don't think I can finish this in 2 minutes. So instead of doing that, let me just show you one more thing that's really interesting about this, the flux, the Stokes theorem. So let's say you had some open surface, some weird looking open surface, and orientation doesn't really matter, but let's give it an orientation. So if it's oriented going outward like this, then the orientation of our surface looks like that, of our sphere, or of our boundary. So if you are asked to find the flux of the curl of some vector field over the surface, Stokes theorem allows us to take the line integral over the boundary of the vector field itself, right? But if you're looking at this and thinking, wow, this looks kind of difficult, so what if there's really something about the curl of this vector field that makes it kind of easier to evaluate, but the surface just looks too crazy? Why can't we take it from here and find another surface that's a lot nicer, say a disk, give it this orientation, and the orientation, I believe, would be pointing this way. So let's call this surface 2, which is a lot simpler than the original surface that we were dealing with. Right? According to Stokes theorem, this line integral over the closed curve is equal to a double integral of the flux over that new surface that we just created that is way easier to think about than this first surface that we had. So, transitivity property says that these two things are equal to each other. So instead of dealing with a difficult surface, maybe we can simplify the surface as long as we have the same boundary and come up with a nicer integral. Okay, so that's another interesting application for Stokes theorem. All right, so tomorrow I'm going to give you guys a quiz where you're going to be computing line integrals and flux integrals, and it'll be a take-home quiz, and I'm more concerned about the step-by-step process and the work that you would do to evaluate these things rather than the final answer. So that's what I'm going to be looking out for. And it'll probably be 2 quizzes. It might look like 2 line integrals and maybe 1 flux integral and 1 surface integral or something like that. And it'll be a take-home, so you guys can work on it over the weekend. And tomorrow we're going to be talking about our last big theorem. All right, see you guys.